Welcome, my friend. Tonight we're going to explore one of the deepest ideas in science: fields, the invisible structures that shape our universe. Together we'll travel from Newton's gravity to the birth of electromagnetism, through relativity, and finally into the quantum world. Each chapter is designed to help you learn something fascinating while gradually drifting off to sleep. Let's begin. Chapter 1. What is a field? From forces to invisible landscapes. When physicists speak about a field, they mean something that exists everywhere, filling space with values that can change in time. A field is not an object you can hold, but a rule that assigns a quantity to every location. Temperature in a room is a simple example. One number at each point forming a temperature field. Wind over an ocean is a vector field. Each point has an arrow representing both speed and direction. This simple idea becomes the backbone of modern physics, shaping how we describe electricity, magnetism, gravity, sound, and fluids. The concept of a field emerged as a solution to a troubling problem in early science. Newton's law of universal gravitation predicted planetary motion with astonishing accuracy, but it implied that the sun could pull on Earth across empty space instantly, without any medium in between. Many scientists found this troubling. In the 19th century, Michael Faraday reimagined forces not as distant pulls, but as patterns of influence filling the space around charges and magnets. James Clerk Maxwell gave Faraday's vision mathematical precision, showing that electric and magnetic influences spread through fields, not across a void. Fields became the stage on which physical interactions unfold. To understand what this means, imagine trying to measure a field. If you could place a thermometer at every point in a room, you'd map the temperature field. Do the same with tiny arrows showing wind speed and direction, and you'd map a velocity field. In physics, we distinguish scalar fields, which assign one number to each point, from vector fields, which assign both magnitude and direction. Fields can be even more complex, but all share the same principle. They fill space with information. Because fields exist everywhere, the laws that govern them are local. A field at a point evolves in time according to its immediate neighborhood, not according to distant regions all at once. That is why electromagnetic waves, sound waves, and ripples on water take time to propagate. A source disturbance does not influence the entire universe instantly. Its effects spread through the field step by step. The patterns fields create are easy to see in experiments. Place a bar magnet under a sheet of paper sprinkled with iron filings, and the filings arrange themselves into arcs. These are not real strings, but alignments with the magnetic field at each point. Around a positive electric charge, we imagine lines radiating outward, showing the direction a test charge would move. Such visualizations help us understand the invisible landscapes shaping the behavior of matter. Fields also interact with materials. An electric field in glass or water is not the same as an empty space. Molecules shift slightly in response, producing polarization that modifies the field inside. Magnetic fields, too, are altered by materials that align their microscopic magnetic moments. Properties like permittivity and permeability summarize these effects, allowing us to predict how light bends in water or glass. Everyday phenomena like refraction, reflection, and shielding all trace back to fields being influenced by matter. Another way to view fields is through potentials. Imagine a smooth landscape of hills and valleys. The height of the terrain at each point represents the potential, while the slope shows the strength and direction of the field. In electrostatics, a charge naturally rolls downhill in this potential landscape. In Newtonian gravity, masses move toward regions of lower potential. This landscape picture is powerful because it translates mathematics into an intuitive image. Fields guide motion like slopes guide rolling stones. Fields are not just guides, they also store energy. Push two light charges together, and you must do work against their repulsion. That energy is stored in the electric field around them. Release the charges, and the field does work back on them. When an antenna transmits, it does not eject matter into space. It excites a disturbance in the electromagnetic field, which then carries energy outward. Light, radio, and microwaves are traveling ripples in the field, carrying both energy and momentum. Because fields can vary in time, they naturally support waves. In electromagnetism, changing electric and magnetic fields generate one another, producing self-sustaining ripples that travel at the speed of light. In air, changes in pressure propagate outward as sound. On a stretched string, displacements travel as vibrations. In each case, waves are not bits of matter moving from source to receiver, but disturbances in a field. Sometimes waves do not travel but stand still. A violin string under tension vibrates at specific frequencies that form stable patterns. In a room, sound waves can produce regions of loudness and quiet, depending on how the standing patterns form. Microwaves inside an oven create standing fields, which is why food heats unevenly without rotation. These examples reveal how fields can store energy in organized ways, shaped by boundaries. Physicists use compact mathematical tools to describe field behavior. Divergence measures how much a field spreads outward from a point, like water from a spring. Curl measures circulation, like air swirling around a storm. Charges act as sources and sinks for the electric field. Currents produce circulation in the magnetic field. Mass creates gravitational fields in Newtonian physics. These abstract tools allow precise predictions and practical engineering, from designing circuits to shaping magnetic fields in motors. Measuring fields is straightforward once we know what to look for. An electric field is detected by the force it exerts on a small test charge. A magnetic field reveals itself through the torque on a compass needle or a voltage induced in a coil. The gravitational field on Earth is experienced as the acceleration of free fall, the same for all objects regardless of their composition. In each case, what matters is the local influence, the field at that point, not distant details of the system. Fields appear in many branches of physics beyond electromagnetism and gravity. Fluid dynamics treats velocity, pressure, and density as fields governed by local conservation laws. Elasticity theory treats stress and strain inside materials as fields, predicting how solids deform. Heat conduction and diffusion processes are fields evolving over time. Even population models or traffic flow can be described in field-like terms. The unifying principle is that fields capture how extended systems behave point by point, with local rules generating global order. Computers now simulate fields routinely. Space is divided into small cells, each holding numbers for the field values, and the laws governing their evolution step forward in time. Weather forecasting depends on field simulations of air pressure and wind. Antennas, fiber optics, and circuits are designed using electromagnetic field computations. Earthquake science relies on models of stress fields in the crust. In every case, local field laws scale up to predict global behavior. A subtle distinction exists between physical fields and the potentials used to describe them. In electromagnetism, the electric and magnetic fields can be derived from scalar and vector potentials. These potentials are not unique. Different choices, called gauges, can describe the same physical situation. This redundancy hints at deeper symmetries, and though the potentials are not directly observable, they remain indispensable in both classical and quantum physics. Gravity offers a parallel view. In Newtonian mechanics, gravity is treated as a field derived from a potential that becomes deeper near massive objects. The gravitational field points toward lower potential and governs the acceleration of bodies. This picture works well for most practical purposes, though general relativity later replaced it with curved space-time. Even so, the field concept survives as a useful approximation, especially in weak gravity environments like Earth's surface. Classical fields are not the final word. At small scales, quantum behavior emerges, and the field picture must be refined. Yet classical field theory remains extraordinarily successful across vast domains. We design power grids, communication networks, and optical instruments using it. Bridges, aircraft, and satellites are calculated with classical field equations. From orbiting planets to the light entering your eye, classical fields remain the quiet structure behind much of daily life. In essence, a field is an invisible landscape. It fills space, carries energy, guides matter, and evolves by local rules. It is the medium by which the universe communicates change. Around you right now, light fields, sound fields, and gravitational fields are at work, whether or not you notice them. And in a quieter reflection, fields remind us that reality is often hidden in patterns rather than objects. We do not see fields directly, only their influence, yet their presence organizes the world. Even emptiness is not empty but structured. The universe, it seems, prefers to weave itself into continuous fabrics. As you settle into rest, you can let that thought comfort you. Fields will keep shaping the world. Light will travel, air will move, gravity will guide, without your effort. You can let go, breathe slowly, and allow your own body to join these rhythms. The day can slip away gently, leaving only the calm patterns that remain. Chapter 2. Gravity before Einstein. Newton's field of universal attraction. Gravity is the oldest of the great physical forces to be described mathematically, and for centuries it has been both familiar and mysterious. We feel it constantly in the weight of our bodies, in the arc of a thrown stone, in the rhythm of the tides, and in the sweeping dance of the planets. Yet for most of human history, gravity was understood only in the simplest terms. Things fall, heavier objects fall faster, and the heavens move according to rules beyond human reach. It was Isaac Newton who gave gravity its first systematic mathematical form, transforming a familiar experience into a universal law. Newton's insight was radical in its simplicity. He proposed that every particle of matter attracts every other particle with a force that depends only on the product of their masses and the square of the distance between them. This meant that the apple falling from a tree was not a trivial event. It was a small example of the same force that holds the moon in orbit and guides the planets around the sun. For the first time, the heavens and the earth were united under a single law of nature. Before Newton, explanations of motion were largely divided. Aristotelian philosophy had distinguished between the natural motion of objects near Earth, which sought their proper place, and the perfect circular motions of celestial bodies. Johannes Kepler had taken important steps toward unification by showing that planets orbit the sun in ellipses, not circles, and that their speeds change according to precise mathematical rules. Galileo had studied falling bodies and inclined planes, revealing the universality of acceleration on Earth. But it was Newton who connected these strands into a single framework. His law of universal gravitation explained why a stone falls, why the moon does not, and why the planets follow the paths they do. To appreciate Newton's achievement, it helps to see how he formulated the concept of a gravitational field. Although Newton did not use the term field in the modern sense, his mathematics implied it. Imagine a massive body, like Earth, producing an influence that extends outward through space. Any smaller mass placed within this influence experiences a force directed toward the larger mass, with a strength proportional to the inverse square of their separation. By expressing the law in this way, Newton effectively described gravity as if space were filled with a pattern of forces, what we now call a gravitational field. This shift in perspective was essential. Instead of thinking of gravity as an event that happens only when two bodies touch or collide, Newton described it as an invisible structure permeating space itself. This invisible structure could be mapped. One could imagine placing a test mass at different points in space and measuring the force it feels. The collection of these forces is the gravitational field. Near Earth, the field points downward with nearly uniform strength, which is why all objects fall with the same acceleration regardless of mass. Farther away, the field weakens according to the inverse square law. This picture allowed physicists to calculate motions with extraordinary accuracy. With Newton's equations, astronomers could predict the return of comets, the timing of eclipses, and the orbits of planets to a degree unmatched in earlier history. Yet Newton himself was uneasy with one aspect of his theory, the mechanism. How could the sun exert a force on Earth across millions of kilometers of empty space? Newton confessed that he made no hypothesis about the cause. His law described what gravity did, not how it worked. This reluctance would echo through centuries of physics, and it would take Einstein's theory of general relativity to provide a deeper account. But in Newton's time, the law was so powerful and so accurate that it became the foundation of celestial mechanics and practical navigation alike. The inverse square law is more than a convenient formula. It encodes a profound geometrical truth. In three-dimensional space, the surface area of a sphere grows as the square of its radius. If gravity spreads outward equally in all directions, its influence must diminish with distance in exactly the way Newton described. This geometric reasoning helps explain why gravity works as it does and why other fundamental forces also obey similar inverse square relations. Nature seems to reveal its geometry in the way fields diminish over space. Newton's law also explained phenomena that had long puzzled observers. The tides, which rise and fall daily, are caused by the combined gravitational pulls of the moon and the sun acting on Earth's oceans. Using his equations, Newton showed how the difference in gravitational pull on the near and far sides of Earth creates the tidal bulges. The same mathematics explained why the moon is gradually slowing Earth's rotation and drifting slowly away over time, a process still measurable with modern instruments. The law was also central to astronomy's triumph in the Enlightenment era. Edmund Halley used it to predict the return of the comet that now bears his name. Pierre-Simon Laplace applied it to the stability of the solar system, showing how complex planetary motions emerge from simple gravitational interactions. Even the discovery of Neptune was made by applying Newton's equations. Astronomers noticed irregularities in Uranus's orbit and deduced the presence of an unseen planet tugging on it. When Neptune was observed in the predicted position in 1846, it was celebrated as a victory of Newtonian mechanics. The field picture clarified another subtlety: superposition. The gravitational field due to multiple masses is the sum of the fields due to each one individually. This principle meant that astronomers could account for the combined effects of all planets on one another, leading to corrections and refinements in orbital predictions. It also explained why the net field inside a uniform spherical shell of matter is zero, an elegant result that finds applications from astrophysics to engineering. But while Newtonian gravity was enormously successful, it also had limits. For one, it assumed instantaneous action at a distance. If the sun were suddenly to vanish, Earth would supposedly feel the change in gravity immediately. This contradicted later understandings of finite propagation speeds. It also could not fully explain the precise motion of Mercury's orbit, which deviates slightly from Newtonian predictions. These issues would later be resolved by Einstein's general relativity, where gravity is not a force acting across space, but the curvature of space-time itself. Still, Newton's field model remained accurate enough to guide centuries of exploration, from the trajectories of cannonballs to the voyages of spacecraft. The idea of gravitational potential added further depth. In Newtonian mechanics, one can describe the field not just as a force, but as the gradient of a potential energy landscape. Near Earth, this landscape is simple. Potential decreases as you go downward. In space, it becomes more complex, shaped by the contributions of many bodies. Spacecraft use this to their advantage, falling into and out of gravitational wells to gain or lose energy, a technique known as gravitational assist. These maneuvers, calculated with Newtonian equations, allow us to reach distant planets with far less fuel than would otherwise be required. Gravity also revealed its power in shaping the cosmos itself. Newton realized that if matter is universally attractive, then in an infinite static universe, everything should collapse together. This apparent paradox troubled him, and he speculated about balancing conditions that might hold the cosmos steady. The problem would not be solved until centuries later with modern cosmology, but even in Newton's time, it hinted at the vast implications of universal gravitation. The same law that explained a falling apple seemed to demand an explanation for the structure of the entire universe. One of the remarkable features of Newtonian gravity is its universality. Unlike electricity or magnetism, which depend on charge or orientation, gravity acts the same way on all matter. Every mass attracts every other mass. This universality is why Galileo's observation that all bodies fall at the same rate fits seamlessly into Newton's framework. It is also why orbits can be predicted without knowing the composition of planets or stars. Gravity cares only about mass and distance. Even today, Newtonian gravity remains indispensable. Engineers designing bridges, architects calculating load-bearing structures, and scientists predicting satellite trajectories all rely on it. General relativity may refine the picture, but for most practical purposes, Newton's field equations are more than adequate. The success of GPS satellites, for instance, depends on corrections from relativity, but their basic orbits are governed by Newton's laws. From space exploration to everyday life, Newton's gravitational field still shapes the world. Stepping back, what Newton offered was a vision of nature bound by a single principle. The force that draws an apple downward is the same force that holds Earth in orbit. The invisible structure of the gravitational field ties together the motions of the smallest and the largest bodies. It was a unification of the everyday and the cosmic. And in that unification lies an existential thought. The same invisible pull that shapes galaxies is pressing gently on you now. You are connected to the sun, to the distant stars, and to every grain of matter in the universe through this field of attraction. You are not separate from the cosmos. You are woven into its fabric by the most ancient of forces. As you prepare to rest, let that be a calming thought. Gravity will continue its quiet work, guiding planets, pulling the tides, and keeping your body cradled against the earth. You do not need to hold yourself up. The universe is already holding you. Let the day release its weight and allow yourself to sink gently into stillness, carried safely by the same law that moves the stars. Chapter 3. The Birth of Electromagnetic Fields. The 19th century marked a turning point in physics, when electricity and magnetism, once seen as distinct curiosities, were revealed to be two aspects of the same phenomenon. Their unification into the concept of the electromagnetic field was one of the most profound achievements in science, reshaping both our theoretical understanding of nature and our practical ability to harness it. The electromagnetic field is now recognized as one of the fundamental pillars of physics, but its emergence was gradual, built from careful experiments, imaginative models, and eventually a set of equations that changed the world. For centuries, electricity and magnetism were treated as unrelated. Electricity was known in its simplest form as static charge, rubbed amber attracting bits of straw, sparks leaping from a cat's fur on a dry day. Magnetism was familiar through lodestones that aligned with Earth's poles and guided sailors across oceans. While both phenomena inspired wonder, they belonged to different traditions of study. Electricity seemed to deal with charged bodies and the shocks they produced. Magnetism seemed tied to mysterious materials with hidden powers. It was only through systematic experimentation that connections began to appear. In the early 19th century, Hans Christian Ørsted made a discovery that began to merge these worlds. In 1820, while lecturing, he noticed that a compass needle deflected when placed near a wire carrying an electric current. This showed that electricity in motion could produce magnetic effects. André-Marie Ampère soon expanded on this, formulating laws that described how electric currents create magnetic fields and how those fields exert forces on one another. Magnetism was no longer mysterious. It could be generated by electricity. The next step came from Michael Faraday, a self-taught experimental genius. Faraday discovered electromagnetic induction in 1831, showing that a changing magnetic field can produce an electric current. He wound coils of wire around iron rings and observed that when current flowed through one coil, a current was momentarily induced in the other. The effect occurred not because of direct contact, but because a changing magnetic environment created an electric influence. This was revolutionary. Electricity could create magnetism, and magnetism could create electricity. Nature revealed a symmetry waiting to be understood. Faraday introduced a new way of thinking to explain these results. He imagined the space around charges and magnets as filled with lines of force. These lines were not just geometric conveniences, but physical realities to him, embodying how nature transmits influences. Where earlier scientists had spoken of invisible forces acting at a distance, Faraday insisted that the region between objects was active. The field was not a void. It was a structured medium capable of storing and transferring energy. His drawings of curved lines emanating from charges and encircling magnets captured an intuition that would prove essential. While Faraday's qualitative ideas were powerful, it was James Clerk Maxwell who gave them mathematical form. Maxwell synthesized experimental laws into a set of equations that described how electric and magnetic fields evolve and interact. Published in the 1860s, these equations unified the phenomena of electricity, magnetism, and optics. For the first time, light itself was recognized as an electromagnetic wave, a ripple in the intertwined electric and magnetic fields propagating through space at a finite speed. What had seemed separate, the shock of a spark, the pull of a magnet, the glow of a flame, were now woven into one fabric. This discovery was profound. Maxwell showed that a changing electric field generates a magnetic field, and a changing magnetic field generates an electric field. The two are inseparably linked, each giving rise to the other. This self-sustaining cycle allows electromagnetic waves to travel through empty space, requiring no medium like air or water. When the equations predicted the speed of these waves, the number matched the measured speed of light. Maxwell concluded that light is an electromagnetic phenomenon, a traveling disturbance in the electromagnetic field. The implications were immense. The electromagnetic field was not just a tool for calculation, it was a physical reality filling all of space. Light from the sun, radio waves carrying human voices, X-rays revealing bones, all of these were now understood as different expressions of the same field. What we perceive as color is the brain's interpretation of electromagnetic waves of varying frequency. What we use in communication technologies are controlled ripples in the field, deliberately generated and captured. Maxwell's work transformed our picture of nature and laid the groundwork for modern physics and engineering. The field concept also explained why energy could be transmitted across space. An antenna emits electromagnetic waves that travel outward, carrying energy and momentum. These waves do not require physical matter to move along. They are sustained entirely by the field itself. Heinrich Hertz demonstrated this experimentally in the late 1880s, generating radio waves and detecting them with simple apparatus, confirming Maxwell's predictions. What began as abstract equations became a tangible reality that shaped the 20th century. To understand why Maxwell's unification was so powerful, consider the situation before him. Electricity and magnetism had separate sets of laws. Electrostatics described charges at rest. Magnetostatics described steady currents in their fields. Induction showed connections, but there was no framework tying it all together. Maxwell provided that framework. His equations showed that electricity and magnetism are not independent. They are aspects of one field described by a unified theory. Just as Newton had brought together celestial and terrestrial motion under gravity, Maxwell united electricity, magnetism, and light. The electromagnetic field also introduced the idea that the medium of propagation was not material in the usual sense. Scientists of the 19th century struggled with this, postulating a substance called the ether that filled space and carried electromagnetic waves. Experiments later showed that no such ether exists. Instead, the field itself is fundamental, not something moving through a medium, but a structure of reality itself. This insight reshaped physics, preparing the ground for relativity and quantum theory. Maxwell's work highlighted the richness of fields compared to simple action at a distance. In his picture, the field has energy, momentum, and stress. It can exert pressure, carry radiation, and transfer forces without direct contact between objects. When sunlight warms your skin, it is because electromagnetic fields traveling across millions of kilometers have carried energy from the sun to you. This energy flow can be calculated precisely as it streams through space, emphasizing that the field is not a mathematical convenience, but a genuine entity. The technology enabled by these discoveries changed human life. Electric power generation and distribution rely on electromagnetic induction. Motors, transformers, and generators are all embodiments of Faraday's and Maxwell's principles. Communication systems, from telegraphs to radio and eventually Wi-Fi, rest on the propagation of electromagnetic waves. Medical imaging, lasers, and fiber optics all extend from the same field equations. The electromagnetic field, once an abstract unification of sparks and magnets, has become the invisible infrastructure of modern civilization. At the same time, the birth of the electromagnetic field deepened our philosophical understanding of nature. It showed that reality is not built solely from particles pushing on one another, but also from continuous fields shaping the environment everywhere. The field became the new foundation, a medium through which information, energy, and structure are carried across the cosmos. In modern physics, even quantum mechanics builds upon this legacy, extending the classical field into the strange territory of quantization. But it all began with the realization that electricity and magnetism are not separate, but two expressions of the same underlying unity. This unity has a quiet elegance. The equations that describe the electromagnetic field are symmetrical, meaning they treat electricity and magnetism in balanced ways. They also respect the finite speed of propagation, ensuring that changes ripple outward at the speed of light rather than instantaneously. This restored a sense of causality to nature. Influences take time to spread, and the field is the medium of their travel. Looking back, the birth of the electromagnetic field was a second great unification in physics, comparable to Newton's unification of falling apples and orbiting planets. Newton tied together the earthly and celestial through gravity. Maxwell tied together electricity, magnetism, and light into one coherent whole. Each unification revealed a deeper simplicity hidden beneath apparent variety. And here lies a quiet reflection. Every time you see light streaming through a window or hear a voice transmitted across the air, you are experiencing the electromagnetic field in action. This field does not belong to one place. It stretches everywhere, binding you to the sun, to the distant galaxies, and to the devices in your hand. The glow of a candle, the colors of the sky, and the signals that carry human words are all woven into its fabric. As you let the day come to an end, you can allow that thought to soothe you. The same field that carries the warmth of the sun has been at work since long before you were born, and it will continue long after. It flows quietly around you now, filling the room with invisible structure, linking you to the wider universe. Let yourself rest within it, breathing gently, while the electromagnetic field goes on with its ceaseless, silent work. Chapter 4. Energy Stored in Fields. One of the most striking realizations in physics is that fields are not merely invisible guides for motion. They are also repositories of energy in their own right. A field is not just a pattern in space. It is capable of storing energy, transmitting it, and even exerting pressure. This idea emerged gradually in the 19th century as scientists sought to understand where energy resides when forces act at a distance, and it remains central to modern physics and engineering. Without the concept of energy stored in fields, the functioning of everything from electrical power systems to the life-giving light of the sun would remain mysterious. To see why this idea matters, imagine holding two like electric charges near each other. As you push them closer, you feel resistance. Work is required to compress them against their mutual repulsion. Where does the energy you expend go? It cannot vanish. In Newton's framework, energy is conserved, so the work must be stored somewhere. The answer, revealed by field theory, is that the energy resides in the electric field surrounding the charges. Similarly, when you separate opposite charges, you also invest energy in the field. Later, if the charges are released, the field does work in return, accelerating them. The field acts as a kind of bank account for energy, keeping track of what has been invested and what can be withdrawn. The same reasoning applies to magnets. Bring two bar magnets together, and you feel them resist alignment one way while snapping together another way. Energy is required to force them into unfavorable configurations, and that energy is stored in the magnetic field they generate. When the magnets are released, the stored energy reappears as motion. The field itself is the intermediary, not just the abstract backdrop for forces. This insight was developed most clearly by James Clerk Maxwell, who showed that electromagnetic fields have an energy density, a certain amount of energy per unit volume of space. This was revolutionary. Space itself, even if apparently empty of matter, could carry energy if it contained a field. The strength of the electric and magnetic fields at each point determines how much energy is stored there. The energy is not in the particles alone, but distributed across the field in space. One of the most direct demonstrations of this idea comes from electromagnetic waves. A radio transmitter, for example, does not shoot material objects outward. Instead, it sets up oscillating electric and magnetic fields that detach and propagate away as waves. Those fields carry energy through space until they are absorbed by an antenna, which converts the field energy back into electrical currents. Light from the sun behaves the same way. The sun emits waves of electromagnetic fields that travel through the vacuum of space, carrying enormous amounts of energy across millions of kilometers before reaching Earth. The warmth you feel from sunlight is the transfer of energy stored in the field. The fact that fields can carry energy also implies that they can exert pressure. When electromagnetic radiation strikes a surface, it pushes on it ever so slightly. This effect, called radiation pressure, is tiny in everyday contexts, but measurable. It becomes significant in astrophysics, where light from stars can drive the motion of gas and dust, shaping the evolution of galaxies. Engineers have even proposed spacecraft propelled by large sails pushed by sunlight, harnessing the momentum carried by the electromagnetic field. The field, intangible though it seems, can exert real mechanical influence. Gravity in the Newtonian sense can also be interpreted as storing energy. When you lift an object against Earth's pull, you do work and increase its gravitational potential energy. Although Newton himself did not describe this in terms of fields carrying energy, later developments showed that one can treat the gravitational field as an energy reservoir. The concept became richer with general relativity, where gravitational waves themselves carry energy across the universe. When two black holes merge, ripples in space-time radiate away vast amounts of energy, detectable on Earth with exquisitely sensitive instruments. Even gravity, the most ancient of forces, reveals itself as capable of storing and transmitting energy through its field. The idea of energy stored in fields is also critical for understanding stability in matter. Consider a capacitor, two conducting plates separated by an insulating gap. When a voltage is applied, charges accumulate on the plates, creating an electric field between them. That field stores energy. If the capacitor is connected to a circuit, the energy can be released later, producing current. Capacitors are used everywhere in technology, from smoothing power supplies to enabling flash photography. They work because energy can reside in an electric field, waiting to be drawn upon. Similarly, inductors store energy in magnetic fields. When current flows through a coil of wire, a magnetic field forms around it. If the current changes, the field resists the change, temporarily storing or releasing energy. This property underlies transformers, motors, and countless electronic devices. Together, capacitors and inductors form the building blocks of modern electrical engineering, their usefulness rooted in the fact that fields are energy carriers. Energy stored in fields also explains the behavior of waves in media. When sound travels through air, part of the energy is kinetic, in the motion of molecules, and part is potential, in the compression of the medium. In an electromagnetic wave, the energy oscillates between electric and magnetic fields. This interplay sustains the wave as it propagates. The recognition that fields themselves hold energy made this explanation possible. The concept extends into more subtle territories as well. The stress that fields can exert within themselves, known as field stress, allows them to pull or push on charges and currents not merely as forces at points, but as distributed influences. Maxwell described the energy and momentum of the electromagnetic field using quantities that showed how energy flows through space. The Poynting vector, though we need not express it mathematically here, represents the flow of energy carried by the field. This idea makes precise our intuition that sunlight carries energy across empty space and that antennas exchange energy with the fields they emit or absorb. The reality of energy stored in fields was dramatically confirmed by the success of technologies that depend on it. Radio transmission, radar, microwave ovens, and fiber optics all rely on electromagnetic waves carrying energy. The reliability of these technologies shows that fields are not just calculational devices, but genuine physical entities capable of storing and transmitting real energy. The implications reach into the cosmos. The energy carried by light from distant stars and galaxies travels immense distances without dissipating into nothingness. Those fields bring us information about the universe, while also transporting the energy that powers photosynthesis on Earth. The very possibility of life depends on the storage and transfer of energy in electromagnetic fields. Without them, sunlight would not warm the planet or fuel the cycles that sustain ecosystems. Even in daily life, the presence of field energy surrounds us constantly. When you turn on a light switch, you are tapping into energy that has been transported across long distances by electric and magnetic fields in power lines. The field guides the flow of electrons and stores energy temporarily in capacitors and inductors along the way. When you listen to a radio, the energy in distant fields has been captured and converted into sound. When you use a smartphone, antennas are continuously exchanging energy with the surrounding electromagnetic field, linking you invisibly to towers and satellites. We live immersed in these reservoirs of energy, though we rarely think of them as such. At the frontier of physics, the idea of field energy raises subtle questions. In quantum theory, even the lowest energy state of a field is not empty, but contains fluctuations, a background often called zero-point energy. These fluctuations are small but unavoidable, hinting that the fabric of space itself may be restless. While this belongs to the quantum picture, it echoes the classical insight. Fields are not inert. They always have the capacity to store and exchange energy. Stepping back, one sees a unifying picture. Fields are not just mathematical descriptions of forces, but physical realities that carry energy, momentum, and structure. They enable objects to interact across space, allow waves to propagate without material support, and give rise to technologies that define modern civilization. The recognition of field energy completed the shift from a universe of particles tugging on each other to one of continuous media shaping interactions everywhere. And in that recognition lies a quiet reflection. The warmth of the sun on your skin, the whisper of a radio signal across continents, the glow of a screen in the evening. All of these are manifestations of energy stored in fields. You are surrounded, even now, by invisible reservoirs silently carrying the forces of nature. They extend through the room, across the planet, and into the cosmos, linking you to events unimaginably far away. As the day draws to its close, you can let this knowledge ease you. The fields will continue their work without your effort, storing and releasing energy, moving light and sound, binding the universe together in silence. You can rest in the assurance that the same laws that carry starlight across the void will carry you into sleep. Let go, breathe softly, and allow the invisible energies to cradle you as the world drifts into quiet. Chapter 5. Fields and Waves: How Vibrations Travel Through Space. One of the most beautiful insights in physics is that fields, once established as real physical entities, can do more than store energy or exert forces. They can vibrate, oscillate, and transmit disturbances across space as waves. Waves are nature's way of moving information and energy without transporting matter itself. They are rhythmic patterns that arise when a system can both store and exchange energy. In fields, this exchange can happen between different parts of the field or between coupled quantities like electric and magnetic components. The result is the phenomenon of waves, which appears in every corner of the physical world. To appreciate the role of waves in fields, it is useful to begin with more familiar mechanical waves. Imagine a stretched string fixed at both ends. If you pluck it, the string vibrates. Each small section of the string is displaced upward or downward and is pulled back by tension. As one section moves, it pulls on its neighbors, and the disturbance propagates along the string. The string itself does not travel from one end to the other. What travels is the pattern of motion, the wave. In air, sound behaves similarly. A vibrating source, like a vocal cord or a tuning fork, compresses and rarefies the surrounding air. These pressure variations move outward, carrying sound energy, though the air molecules themselves only oscillate slightly around their average positions. The leap to fields is natural. Once we recognize that fields can store energy, it follows that they can support vibrations where energy oscillates between different forms. In an electromagnetic field, the electric component and the magnetic component exchange energy back and forth. A changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. Together they form a self-sustaining pattern that can detach from its source and travel outward as a wave. This is what Maxwell's equations revealed in the 19th century. The electromagnetic field is not static but dynamic, capable of carrying waves through empty space. The electromagnetic wave is unlike mechanical waves, which require matter to travel through. Sound needs air or another medium. Water waves require a liquid surface. But electromagnetic waves do not need a medium. They can propagate through the vacuum of space, their electric and magnetic components sustaining each other. This is why light from distant stars reaches us across the emptiness between galaxies. It is why radio transmissions can span continents, and why spacecraft receive signals billions of kilometers from Earth. The field itself is the carrier, needing nothing beyond its own structure. The physics of waves in fields can be understood in terms of oscillation and propagation. When a localized disturbance occurs in a field, the information about that disturbance does not remain confined. Local rules dictate that changes influence neighboring points, and those points influence their neighbors in turn. The result is a ripple spreading outward. Because fields extend everywhere, such ripples can travel long distances. The mathematics describing this process is the wave equation, a general relation that emerges in contexts as varied as strings, fluids, and electromagnetism. Though the details differ, the essential feature is the same. Localized energy becomes distributed through oscillations that travel. An especially important distinction exists between transverse and longitudinal waves. In a transverse wave, the disturbance is perpendicular to the direction of travel. On a string, when you move your hand up and down, the wave travels horizontally while the displacement is vertical. Electromagnetic waves are transverse too. The electric and magnetic fields oscillate at right angles to the direction of propagation. In contrast, sound waves in air are longitudinal. The oscillations of pressure occur along the same direction the wave travels. This distinction shapes how different waves interact with matter and how they carry information. The ability of fields to carry waves explains much of what we observe in the natural world. Light is the most familiar electromagnetic wave, spanning the spectrum from infrared warmth to visible colors to ultraviolet radiation. But the same field also supports radio waves, microwaves, X-rays, and gamma rays, all differing only in frequency and wavelength. The diversity of phenomena, sunlight warming your skin, radio connecting continents, X-rays imaging bones, arises from a single field vibrating across scales. The unity of these processes underscores the power of the wave concept. Fields can also sustain standing waves. These occur when waves reflect and interfere in such a way that certain points remain stationary while others oscillate strongly. In musical instruments, standing waves on strings and air columns produce resonant tones. In electromagnetic cavities, standing waves determine the operation of lasers and microwave devices. These resonances arise because fields, when confined by boundaries, settle into patterns where oscillations reinforce themselves at specific frequencies. The interplay between structure and vibration produces order from what might otherwise be random motion. The energy carried by waves in fields can be transmitted over great distances. When sunlight travels from the sun to Earth, it carries not only illumination, but also the energy that powers weather, fuels ecosystems, and sustains life. This transfer of energy is efficient and continuous, requiring no medium to degrade it. The same principle applies when radio waves carry information. Oscillations at a transmitter generate field vibrations that travel outward, encoded with patterns representing voices or data. An antenna far away captures the oscillations and converts them back into electrical signals. Across vacuum, across continents, the field carries waves that link distant places and moments. Waves also reveal the subtlety of interference and diffraction. When two waves overlap, their effects add together. Sometimes they reinforce, producing bright regions or loud sounds. Sometimes they cancel, producing darkness or silence. In fields, this interference pattern can be incredibly rich. Light waves passing through slits create intricate fringes on a screen, demonstrating that even particles like photons obey wave principles. In radio communication, interference can enhance or disrupt signals, requiring careful engineering. These effects highlight the reality that waves are not isolated objects, but overlapping patterns in a shared medium. Another striking aspect of field waves is polarization. In electromagnetic waves, the electric field can oscillate in different orientations. Polarization determines how the wave interacts with matter. Sunglasses that block glare use polarization filters to reduce specific orientations of light. Antennas are designed to match the polarization of incoming radio waves for maximum efficiency. The orientation of the wave's oscillation, though invisible to the eye, is a real and measurable property, showing the richness of the field's vibrational possibilities. The universality of wave behavior suggests something profound. Whether in strings, air, water, or fields, the same mathematical patterns appear. Waves reflect, refract, interfere, and diffract according to principles that do not depend on the specific system. The field perspective extends this universality into the very fabric of space. Oscillations in electromagnetic fields and even in gravitational fields, as shown by gravitational waves, obey the same logic. The cosmos is full of vibrations, from the ripples of starlight to the faint shivers of space-time itself. Technological applications of field waves are everywhere. The electrical grid relies on alternating current, which is essentially a standing electromagnetic wave oscillating through wires and transformers. Wireless communication depends on controlled electromagnetic vibrations carrying encoded information. Medical imaging uses field waves to probe the body, whether through radio waves in MRI or high-frequency electromagnetic waves in X-rays. Even the quiet glow of a light bulb is field energy carried by oscillations of charges and released as waves. Our lives are threaded with the practical fruits of understanding fields and waves. The concept reaches beyond electromagnetism. Fluid dynamics describes waves in pressure and velocity fields, producing ocean swells and atmospheric sound waves. Earthquakes send seismic waves through the planet, vibrating the elastic field of rock. These are reminders that the wave phenomenon is not confined to one type of field, but is a general expression of how continuous systems behave when disturbed. The universe resonates with wave activity across every scale. At the deepest level, the wave nature of fields invites reflection. A wave is neither the medium nor the disturbance alone. It is the pattern that emerges when the two interact. It is real but intangible, structured yet ephemeral. Waves carry energy and information, linking distant points without moving material between them. They embody a paradox of presence without substance, influence without contact. And in this paradox lies an existential thought. You are surrounded by waves at every moment, light filling the room, sound shaping the air, fields vibrating invisibly to carry signals. You are immersed in patterns that connect you to the wider universe, threads of rhythm tying you to the sun, the stars, and to other human beings across vast distances. The world is not silent, but filled with endless vibrations, woven into the fabric of space. As the day closes, let this awareness settle gently. Just as fields vibrate and release their stored energies in graceful patterns, you too can let your thoughts ripple outward and then fade. You do not need to hold the day's burdens tightly. Like waves, they can pass, leaving calm behind. Let yourself sink into rest as the quiet oscillations of the universe continue their steady dance around you, carrying on their work while you sleep. Chapter 6. Relativity Meets Fields, the Electromagnetic Field Tensor. By the middle of the 19th century, James Clerk Maxwell's equations had unified electricity, magnetism, and light into a single framework. But while Maxwell's theory was an extraordinary success, it left behind deep puzzles about how electromagnetic fields relate to space and time themselves. The late 19th and early 20th centuries saw physics undergo a conceptual transformation, as Einstein's theory of relativity revealed that space and time are not absolute, but interwoven into a four-dimensional continuum. Within this new framework, the electromagnetic field took on a new, more elegant form. What once appeared as separate electric and magnetic fields became recognized as different perspectives on the same physical entity, the electromagnetic field tensor. To understand why this step was necessary, consider the old Newtonian view. In classical mechanics, time was assumed to be universal, ticking the same everywhere, and space was considered an immutable stage where events unfolded. The speed of light was thought to depend on the medium, much like the speed of sound depends on air. Maxwell's equations, however, predicted something different. They showed that electromagnetic waves propagate through space at a fixed speed, determined by the electric and magnetic constants of free space. Experiments confirmed that this speed is the same no matter how the source or the observer moves. This was difficult to reconcile with the Newtonian worldview. If light always traveled at the same speed, then either space and time had to behave differently than previously imagined, or Maxwell's theory was incomplete. The famous Michelson-Morley experiment in 1887 sought to measure Earth's motion relative to the hypothetical luminiferous ether, the supposed medium for light waves. If such a medium existed, then light moving along Earth's motion should appear at a different speed compared to light moving across it. Yet no such difference was detected. Light's speed appeared to be invariant. The failure to detect the ether set the stage for Einstein's 1905 theory of special relativity, which abandoned the notion of an absolute medium and instead made the constancy of the speed of light a fundamental principle. Einstein's theory introduced a radical idea. Space and time are not separate absolutes, but components of a unified space-time. Events are described by 4 coordinates, 3 of space and 1 of time, woven together into a continuum where distances and durations depend on the observer's motion. Within this framework, physical laws must be expressed in ways that are the same for all observers moving at constant velocities. Maxwell's equations, when recast in this language, fit perfectly. Relativity did not overthrow Maxwell's theory. It revealed its deeper structure. In this new space-time picture, the electric and magnetic fields could no longer be treated as distinct entities. Instead, they are combined into a single mathematical object, the electromagnetic field tensor. While the tensor itself is a compact mathematical construct, its meaning is straightforward. It organizes the electric and magnetic components into a unified whole, ensuring that the laws governing them remain consistent across all reference frames. What one observer perceives as a purely electric field, another observer in motion might perceive as a mixture of electric and magnetic fields. The tensor encodes this relativity of perception, capturing the field in a way that is independent of any single observer's viewpoint. This unification explains puzzling effects in a natural way. Imagine a wire carrying an electric current. In the wire's rest frame, it appears electrically neutral, with positive charges in the metal balanced by moving electrons. But to an observer moving alongside the electrons, the spacing between charges changes due to relativistic effects, and the wire now appears electrically charged. What was purely a magnetic field in one frame becomes partly electric in another. The electromagnetic tensor describes both at once, showing that magnetism is, in a sense, electricity viewed through the lens of relativity. The elegance of this approach is that the laws of electromagnetism take on a remarkably compact form in spacetime. Maxwell's equations, which once seemed like separate laws for electric and magnetic phenomena, become unified into a small set of tensor equations that are manifestly consistent with relativity. The complexity dissolves when viewed in the proper framework. Fields and waves that once seemed separate phenomena emerge as different facets of the same underlying structure. Relativity also clarified how energy and momentum flow in electromagnetic fields. The stress-energy tensor, another mathematical object, describes how fields carry energy, exert pressure, and transfer momentum in space-time. Light waves, for example, are not just vibrations but streams of energy encoded in the field. Their impact on matter, whether in the gentle push of radiation pressure or the violent energy release of stellar fusion, can be described precisely within this formalism. The field tensor and the stress-energy tensor together provide a complete account of how fields behave in relativity, linking geometry, energy, and force. The connection between electromagnetism and relativity is not merely mathematical but deeply physical. Without relativity, the symmetry between electricity and magnetism is incomplete. Only when we accept that space and time are interwoven do the transformations between electric and magnetic fields make sense. Magnetism itself can be seen as a relativistic correction to electricity. The fact that moving charges give rise to magnetic forces is not a separate law, but a consequence of how electric fields transform when viewed in different frames of motion. This realization ties two seemingly distinct forces into one continuous reality. The electromagnetic field tensor also opened pathways to more advanced theories. It set the stage for general relativity, where gravity is described not as a force but as the curvature of space-time. The idea that fields are best understood through tensors in space-time proved so fruitful that it became the standard language of modern physics. Later, in quantum field theory, the electromagnetic tensor survives as the classical limit of a quantized field, bridging the old and the new. The clarity of this formulation underscores how deeply relativity reshaped our view of fields. The experimental confirmation of relativity's predictions strengthened the case. Time dilation and length contraction, once counterintuitive ideas, became measurable realities. High-speed particles in accelerators live longer than expected because their internal processes slow down relative to the laboratory frame. GPS satellites must correct for both special and general relativistic effects to provide accurate navigation. And electromagnetic fields behave exactly as predicted when transformed between frames, validating the tensor formulation. These practical consequences show that relativity is not an abstraction, but an essential part of the real world. At a human scale, the electromagnetic field tensor may seem remote, a mathematical entity belonging to textbooks, yet its implications surround us constantly. Every time you use wireless communication, you are participating in the interplay of electric and magnetic fields that transform consistently under relativity. The fact that signals travel at the speed of light, unaffected by the motion of Earth or the receiver, is built into the structure of space-time itself. The global web of communication depends on these principles functioning flawlessly, day and night. The fusion of relativity and electromagnetism also carries a deeper philosophical resonance. It shows that the divisions we perceive in nature, electric versus magnetic, space versus time, are not absolute. They are perspectives within a more unified whole. What looks like separation is often unity seen from a limited vantage point. This echoes a broader lesson of science. Reality is often simpler and more connected than our initial intuitions allow. And here lies an existential reflection. The same laws that merge electricity and magnetism into one field also merge space and time into one fabric. The universe is not divided as neatly as we imagine. It is a continuous whole where distinctions blur when examined closely. In that sense, your own experience of time and place is part of a larger unity, woven into the same fabric that carries starlight and sustains the signals linking humanity together. As you prepare to leave this day behind, you can take comfort in that thought. The fields around you will continue their ceaseless transformations, carrying light and energy, indifferent to the small concerns of daily life. Space and time themselves hold you within their structure. You can release the weight of the day, knowing that the same laws that govern the galaxies also guide the quiet fields in the room. Let yourself breathe slowly, let go of your burdens, and drift into the calm rhythm of the universe's unbroken fabric. Chapter 7. Fields in Matter. How materials shape invisible forces. So far, we have spoken of fields as if they lived freely in space, spreading out from charges and currents, carrying energy and sustaining waves even through the vacuum. But in practice, we rarely encounter fields in pure empty space. Almost always they pass through or interact with matter, air, glass, water, metals, biological tissue, the very materials of our world. And when they do, the fields change. They bend, slow down, become concentrated, or weaken. Materials respond to fields, and in turn, fields shape the behavior of matter. This interplay is one of the richest and most practical aspects of classical field theory, underlying technologies from lenses to power grids, from wireless communication to medical imaging. The simplest way to see this is with light passing from air into water. To the eye, a straw in a glass of water looks bent at the surface. A fish beneath the waves does not appear where it truly is. This bending of light is refraction, and it happens because the electromagnetic field interacts differently with water than with air. The speed at which light propagates depends on the medium. In a vacuum, light travels at its maximum speed. In glass or water, the field couples to the charged particles inside the material, which respond by oscillating and re-radiating. The combined effect is a delay in the propagation of the wavefront, so the effective speed is reduced. This slowing changes the direction of the wave when it crosses from one medium into another, giving rise to the familiar bending effect. Refraction is just one aspect of how materials shape fields. When light passes through a prism, the bending depends on wavelength, which is why white light splits into a rainbow of colors. Each frequency of light interacts differently with the electrons in the glass, so the field's propagation speed depends on color. This dependence is called dispersion, and it explains why rainbows appear in the sky. Raindrops act as tiny prisms, refracting sunlight into its constituent colors. Without the interaction between electromagnetic fields and matter, such displays would not exist. Materials can also reflect fields. A mirror returns light almost perfectly, not because it is magical, but because the free electrons in the metal rearrange themselves in response to the incoming field, creating a new field that cancels the wave inside the material and sends it back outward. The shininess of metals, the glare of polished surfaces, the echoes of sound against walls, all are examples of fields being shaped by matter's ability to respond and reflect. Transparency, opacity, and color are likewise consequences of how materials interact with fields. Glass is transparent because its electrons do not absorb visible light strongly. Instead, they allow the wave to pass through with only a change in speed. Wood or stone, by contrast, absorb or scatter most visible light, preventing transmission. The green of leaves, the blue of the sky, and the red of a sunset all arise from selective interactions between fields and matter, where some frequencies are absorbed, others transmitted, and still others scattered. What we see as color is the fingerprint of matter's influence on the electromagnetic field. But fields shape matter as much as matter shapes fields. In dielectrics, materials like glass or plastic, an applied electric field polarizes the atoms or molecules. The positive and negative charges within each atom shift slightly, creating tiny dipoles. These dipoles in turn generate their own fields, which alter the overall field distribution inside the material. This polarization reduces the effective field compared to what would exist in a vacuum, and the degree of reduction is characterized by the material's permittivity. This is not just abstract. It determines how capacitors store energy, how lenses bend light, and how waves propagate in fibers that carry the world's internet traffic. Magnetic fields experience similar transformations. In ferromagnetic materials such as iron, cobalt, and nickel, the microscopic magnetic moments of atoms, caused by the spins of electrons, tend to align with one another. When an external magnetic field is applied, these moments can all orient in the same direction, greatly amplifying the field inside the material. This collective alignment is what makes magnets powerful. It also makes transformers and electric motors possible, as magnetic fields in iron cores are guided and strengthened, efficiently channeling energy. Other materials, like diamagnets, respond weakly in the opposite direction, slightly repelling magnetic fields. The diversity of magnetic responses reveals how deeply matter is intertwined with fields. Conductors add another layer to this picture. Metals contain free electrons that can move easily in response to electric fields. As a result, static electric fields cannot penetrate deeply into a conductor. Charges rearrange themselves on the surface, canceling the field inside. This is why a metal cage can shield sensitive equipment from external electric disturbances, an effect known as the Faraday cage. In alternating fields, however, conductors allow currents to flow, dissipating energy as heat or transmitting it as useful power. The way fields distribute themselves in conductors underlies the operation of electrical circuits and power transmission. Fields in matter are not only about passive response, they can also trigger new behaviors. Certain crystals, for example, exhibit the piezoelectric effect. When mechanical stress is applied, an electric field is generated, and conversely, applying an electric field causes the crystal to deform. This property is used in sensors, actuators, and ultrasound imaging. In other materials, light itself can generate electric currents through the photovoltaic effect, the basis of solar cells. These effects demonstrate that matter does not just alter fields, but can convert between field energy and mechanical or electrical forms. Understanding how materials shape fields also allows us to design systems that guide them deliberately. Waveguides, optical fibers, and cavities use carefully engineered materials and geometries to confine fields, direct their flow, and enhance certain frequencies while suppressing others. In an optical fiber, light remains trapped within a thin core of glass, zigzagging through by continuous refraction. This ability to guide fields with precision has revolutionized communication, enabling the internet and global connectivity. The behavior of fields in matter even touches the quantum scale. In semiconductors, electrons move through a crystalline lattice where fields are modified by the periodic structure of atoms. When light interacts with such materials, it can promote electrons to higher energy states, creating currents and powering modern electronics. The combination of field theory with the microscopic properties of matter lies at the heart of solid-state physics, leading to transistors, lasers, and all of modern information technology. The study of fields in matter also reveals subtleties in energy storage and release. In a dielectric material, when an electric field is applied, energy is stored in the polarization of the molecules. If the field is removed suddenly, the stored energy can return to the circuit. In a magnetic material, the alignment of atomic spins represents a reservoir of energy that can be tapped or reversed. These microscopic processes underlie the macroscopic properties of devices we rely on daily. Astrophysics offers grander examples. Fields in matter interact across cosmic scales, shaping galaxies and stars. Magnetic fields threading interstellar gas guide the formation of stars and the dynamics of plasma. In the sun, charged particles interact with intense fields, producing solar flares and storms that can affect Earth. The auroras, dancing curtains of light in polar skies, occur when solar wind particles follow Earth's magnetic field lines into the atmosphere, where they collide with atoms and release photons. These spectacular displays are direct evidence of fields sculpting matter and matter responding in kind. At every level, from the transparent glass in a window to the glow of auroras across the sky, the lesson is the same. Matter and fields cannot be considered separately. Matter shapes fields, altering their paths and strengths. Fields shape matter, inducing currents, polarizations, and alignments. Together, they form the interactive fabric of physical reality. Without this interplay, there would be no color, no lenses, no electricity, no magnetism, no communication, and no life. And here we can pause for a quiet reflection. The invisible forces around you are constantly being shaped by the materials of your world. The walls of your room guide electromagnetic waves, shielding and transmitting. The glass in a lamp bends and filters light. Even your body, filled with water and ions, interacts with fields, responding to the same invisible patterns that govern stars. You are not separate from these interactions. You are part of the web of matter and fields exchanging influence. As the day fades, let this awareness become gentle background. The fields around you will keep flowing, guided by the shapes and textures of the world, whether or not you pay them attention. You can let the day's tensions dissipate, knowing that nature carries on with its ceaseless exchange of energies. Breathe slowly, let go of your worries, and allow yourself to rest, shaped and supported by the same quiet forces that guide the universe. Chapter 8. The Principle of Least Action and Field Lagrangians. As physics matured, scientists searched for deeper unifying principles, ideas that could capture many laws at once and reveal their underlying simplicity. One of the most profound of these principles is the principle of least action. At first glance, it sounds almost philosophical. Nature, when left to itself, chooses the path that requires the least action. But this is not poetry. It is one of the most powerful frameworks in physics, describing the motion of particles, the behavior of fields, and ultimately the structure of the universe. The idea has its origins in mechanics. In the 18th century, Pierre-Louis Maupertuis suggested that nature operates economically, taking paths that minimize effort. This vague notion was given mathematical clarity by Joseph Louis Lagrange and William Rowan Hamilton, who developed a formalism that remains at the core of modern physics. In this view, a system evolves between two states not according to arbitrary rules, but according to a principle. Among all possible histories, the actual one is the one that makes the action stationary, usually minimal, though in precise terms, it is an extremum. Action, in this context, is not ordinary effort, but a mathematical quantity defined as the integral of something called the Lagrangian over time. The Lagrangian itself is a function that encapsulates the energy of the system, typically the difference between kinetic energy associated with motion and potential energy associated with position or configuration. For a simple particle, this is straightforward. For fields, the concept extends, with the Lagrangian density describing how energy is distributed and evolves in space and time. This shift from forces to actions represents a deep change in perspective. Newton's mechanics, with its emphasis on forces causing accelerations, is local and intuitive. But the Lagrangian approach sees the entire path at once, comparing possibilities and selecting the one that makes the action stationary. It is as though nature looks at all possible futures and selects the one most consistent with this principle. Of course, the universe does not literally choose, but the mathematics works as if it did. The result is astonishing. The principle of least action can reproduce Newton's laws, Maxwell's equations, and much of classical and modern physics with one unified method. Fields fit naturally into this framework. Just as a particle has a Lagrangian, a field has a Lagrangian density. This quantity depends on the values of the field and its rate of change across space and time. When one applies the principle of least action to a field, the result is a set of equations describing its dynamics. For the electromagnetic field, using the correct Lagrangian density leads directly to Maxwell's equations. Instead of juggling separate experimental laws, one can derive the entire theory from a single principle. This approach has several advantages. It highlights symmetries, patterns in the laws of physics that remain the same under certain transformations. Through a mathematical connection known as Noether's theorem, symmetries correspond to conservation laws. For instance, if the Lagrangian does not change when time is shifted, then energy is conserved. If it does not change when space is shifted, momentum is conserved. If it does not change when space is rotated, angular momentum is conserved. This is not coincidence. It is a profound truth about nature. The fields, through their Lagrangians, reveal how conservation arises not as an imposed rule, but as a natural consequence of symmetry. One of the most striking aspects of this connection is how general it is. Energy conservation, which seems obvious in daily life, is actually a consequence of the symmetry of time itself. If the laws of physics remain the same tomorrow as they are today, then energy must be conserved. Similarly, momentum conservation follows from the uniformity of space. No place in the universe is fundamentally special. Angular momentum conservation arises from the symmetry of rotations. Turning the entire system around does not change the laws. These conservation laws, which guide everything from the motion of planets to the functioning of machines, are embedded in the very structure of the action principle. The power of the least action principle extends far beyond electromagnetism. Elasticity, fluid dynamics, and even gravity can be described in this way. Einstein's general relativity, for example, can be derived from an action principle involving the curvature of space-time. Quantum field theory, which governs the subatomic world, is also formulated using Lagrangians. In every case, the underlying logic is the same. Write down the action, apply the principle of least action, and obtain the equations of motion. One might ask why the universe follows this principle at all. Why should nature care about minimizing or extremizing some abstract mathematical quantity? The answer is not fully known, but the consistency and success of the framework suggest that it expresses something fundamental. In quantum mechanics, the mystery deepens. Richard Feynman's path integral formulation shows that particles in the quantum world actually explore all possible paths, but their probabilities interfere in such a way that the classical least action path emerges as the one of highest likelihood. In this sense, the principle of least action is not just a convenient rule, but a reflection of how reality operates at both classical and quantum levels. Fields make the story richer because they involve not just single trajectories, but continuous distributions across space. The Lagrangian density assigns a contribution to every point in space and time. By integrating over the entire region, one obtains the total action. Applying the principle then yields equations that ensure the field's evolution is consistent everywhere. This method is powerful because it avoids the need to specify forces point by point. Instead, the field equations emerge naturally from a single compact principle. Consider electromagnetism again. Maxwell's equations can be obtained from a Lagrangian density that involves the electromagnetic potentials and their derivatives. The resulting equations automatically respect the symmetries of spacetime and the gauge freedom inherent in the theory. This is not just elegant but practical. It ensures that the theory is self-consistent and that energy, momentum, and charge are conserved. The principle of least action is not an add-on to field theory, but its very foundation. The role of symmetry here cannot be overstated. Gauge symmetries, which allow the potentials to change without affecting the physical fields, give rise to the conservation of electric charge. This deep link between invariance and conservation is one of the most beautiful results in theoretical physics. It shows that what may appear as separate facts, charge conservation, energy conservation, momentum conservation, are all consequences of symmetry in the action. The universe, at its core, seems to be structured around these principles of economy and invariance. This connection also explains why the Lagrangian method is so fruitful in building new theories. Physicists searching for extensions of known physics, whether in particle physics, cosmology, or condensed matter, begin by writing down a possible Lagrangian. The action principle then generates the equations of motion. If the proposed Lagrangian respects the required symmetries, it automatically guarantees conservation laws. This procedure is so reliable that it has become the main language of modern theoretical physics. Historically, the least action principle represented a philosophical shift as well. To many early thinkers, it seemed to embody an economy of nature, a preference for efficiency. Maupertuis and others even saw it as evidence of divine design. Today, physicists view it as a mathematical truth, yet the sense of elegance remains. The fact that complicated laws reduce to a simple principle suggests that the universe is not random or wasteful, but governed by hidden coherence. Another layer of richness comes when the least action principle is applied in curved spacetime. Einstein's general relativity can be derived from the so-called Einstein-Hilbert action, which involves the curvature of spacetime itself. From this single principle arise the field equations that describe black holes, gravitational waves, and the expansion of the universe. Here, the action principle is not just a mathematical curiosity, but the foundation of our most successful description of gravity. In the quantum domain, the principle of least action also finds new meaning. Feynman's formulation of quantum mechanics, where every possible path contributes to a particle's behavior, shows that the classical path of least action emerges only as the net result of interference. The principle, then, is not merely a heuristic, but a bridge between classical determinism and quantum probability. This illustrates the depth of the idea. It is as if the universe explores every possibility, yet coherence emerges in the form of least action. The universality of the action principle suggests that it may be more than just a convenient formalism. It could be a clue to the deep structure of reality. When physicists attempt to unify forces or propose new fields, they nearly always turn to Lagrangians. This is not just tradition, It reflects the conviction that whatever the ultimate laws are, they too must fit into the economy and symmetry of action. Even speculative ideas like string theory rely heavily on action principles, showing how central they have become. And here lies a quiet reflection. The universe, with all its complexity, may be governed by a principle that values balance and coherence. What looks chaotic may, at its root, be the unfolding of a rule that seeks economy in motion. The least action principle whispers that the world is not driven by randomness alone, but by patterns of symmetry and order. As the day ends, you can take comfort in this thought. Just as fields follow the simplest, most harmonious paths, you too can release unnecessary effort. The work of the day is complete, its actions taken. Now you can let go, trusting that the universe itself moves toward balance. Let your breath fall gently, let your body grow still, and allow yourself to drift, carried by the same quiet principle that guides the stars in the fields. Chapter 9. Classical Field Theories Beyond EM, Fluid and Elastic Fields. When most people hear the term field theory, their thoughts go immediately to electromagnetism or perhaps gravity. These are, after all, the archetypal examples that shape modern physics. Yet the concept of a field extends far beyond them. Fluids, solids, sound waves, and even the stresses in materials are all described most naturally with fields. Long before quantum mechanics and relativity reshaped our worldview, physicists and engineers were already using field concepts to understand how air moves, how oceans swell, and how bridges bend. These classical field theories are less exotic than electromagnetism, but no less profound. They demonstrate that fields are not restricted to invisible forces in empty space, but permeate the matter around us, governing how it flows, vibrates, and resists. Fluids provide one of the clearest examples. At first glance, a fluid might seem like a collection of countless individual particles, molecules of air or water bouncing and sliding past each other. This microscopic picture is accurate, but it is often impractical. For most purposes, what matters is not each molecule, but the collective behavior of billions upon billions of them. To describe this collective motion, we turn to fields. The velocity of a fluid at each point in space and time is a vector field. The pressure is a scalar field, assigning one value everywhere. The density of the fluid is another scalar field. Together, these fields describe the state of the fluid without tracking individual molecules. The equations governing these fields are local, as with all field theories. The change in velocity at one point depends on the nearby pressure gradient, viscosity, and forces applied. The change in pressure depends on how density and velocity vary around it. These relationships are encapsulated in the Navier-Stokes equations, among the most famous and challenging in mathematics. Though their full solutions are notoriously difficult to obtain, the field concept makes them possible to write down at all. Without it, fluid motion would be hopelessly intractable. Consider a river flowing past rocks. The velocity field shows water accelerating around obstacles, slowing in eddies, and tumbling into vortices. Pressure fields rise and fall accordingly, shaping the forces felt on submerged stones and the riverbank. Or imagine air flowing around the wing of an aircraft. The velocity and pressure fields explain how lift is generated, allowing metal machines to soar. Pilots, engineers, and meteorologists rely on these field concepts every day, whether predicting turbulence or designing efficient turbines. Waves in fluids, such as sound, are also elegantly described by fields. A sound wave is a disturbance in the pressure field of air, propagating outward as alternating compressions and rarefactions. The mathematics of wave propagation arises naturally from the fluid field equations. The same framework explains the crash of ocean waves, the whisper of wind through trees, and the vibrations inside musical instruments. All are expressions of fluid fields responding to disturbance. Elastic fields describe the behavior of solids in a similar way. A solid resists deformation, but not absolutely. Push or stretch it, and it responds with internal forces. These forces are captured by the stress field, which records the internal forces per unit area within the material. At the same time, the displacement of particles in the solid defines a strain field. Stress and strain are linked by material properties such as elasticity. The combination gives rise to Hooke's law and to the equations of elasticity, which describe how bridges bear loads, how buildings resist earthquakes, and how bones support bodies. Like fluids, elastic solids support waves. When a hammer strikes a metal rod, waves of compression and tension travel through it. Earthquakes send seismic waves through rock, traveling vast distances to reveal Earth's interior structure. These waves exist because fields of stress and displacement propagate disturbances just as electromagnetic fields do. They can be longitudinal, like sound waves, or transverse, like ripples on a string. Their existence demonstrates the unity of wave phenomena across different types of fields. The practical implications of elastic field theory are vast. Civil engineers use it to design safe buildings, ensuring that stress fields within structures remain below failure limits. Seismologists analyze seismic fields to locate earthquakes and study Earth's inner layers. Materials scientists use it to develop alloys and composites that distribute stress efficiently. At every scale, from nanoscale crystals to tectonic plates, the field approach reveals patterns that govern strength, stability, and change. Fluid and elastic fields are not isolated from one another. In many cases, they interact, producing complex behaviors. The vibrations of a violin string couple to the air around it, turning elastic oscillations into sound waves that fill a concert hall. The motion of ocean water interacts with the seabed, transferring stress fields into erosion and geological change. The air flowing over buildings creates pressure fields that translate into mechanical stresses. These interactions demonstrate how field theories of different types merge into a coherent description of reality. Energy storage in these fields parallels what we saw in electromagnetism. In a compressed spring, energy is stored in the elastic field. Release the spring, and the energy becomes kinetic motion. In a moving fluid, energy exists in the form of kinetic energy density and pressure potential. Waves carry energy across fluids and solids, transporting it without carrying matter long distances. These processes show that the concept of field energy is not confined to invisible forces, but is part of the everyday physical world. The mathematics of these theories also echoes the elegance found in electromagnetism. Differential equations describe how fields change in time and space. Boundary conditions, whether the surface of a pipe, the edge of a bridge, or the seafloor, shape the fields and determine how they evolve. Symmetries and conservation laws emerge here too. Conservation of mass in fluids, conservation of momentum in solids, and conservation of energy in both are direct consequences of the local laws governing fields. These classical field theories also highlight the limits of human intuition. We may find it easy to imagine particles colliding, but fluid turbulence, with its swirling vortices and chaotic eddies, is notoriously hard to predict. Yet even turbulence is governed by local field laws. Likewise, the distribution of stress in a complex structure cannot be guessed by inspection, but the field equations make it calculable. The field concept provides a language more reliable than intuition alone, allowing predictions that save lives and shape technologies. Modern computation has amplified the power of these theories. Numerical simulations divide fluids and solids into grids, calculate field values at each point, and evolve them in time. Weather forecasts rely on simulations of atmospheric velocity, pressure, and temperature fields. Engineering software predicts how skyscrapers sway in winds and how bridges respond to heavy traffic. Ocean models simulate currents, tides, and tsunamis, helping protect coastal communities. Behind each of these practical tools lies the classical field concept, giving structure to what would otherwise be overwhelming complexity. The universality of the field approach invites a broader reflection. Fluids, solids, and electromagnetic waves may seem unrelated, but all obey the same logic. Disturbances propagate through continuous media, energy is stored and transmitted, and local laws determine global behavior. Whether in the crash of a wave, the vibration of a string, or the flexing of a bridge, the mathematics of fields provides clarity. The field idea is not confined to the invisible forces of physics, but is equally at home in the tangible materials of everyday life. Even in the living world, fields of this kind are indispensable. Blood flow is modeled as a fluid field, with pressure gradients driving circulation. Bones and muscles are studied with elasticity theory, ensuring that implants and prosthetics match the stresses of the body. The lungs are analyzed as networks of airways governed by fluid dynamics. These applications show that classical field theories are not abstract, but intimately connected with human health and survival. On the grandest scale, astrophysics too relies on these theories. The atmospheres of planets are fluids shaped by pressure and velocity fields, producing weather systems and climate. Stars vibrate with oscillations that spread as waves, allowing astrophysicists to probe their interiors. Seismic waves from distant quakes ripple through moons and planets, revealing their hidden structures. The field concept unifies Earth and cosmos, showing that the same principles hold from ocean currents to stellar winds. And here lies an existential reflection. The world around you is filled with invisible patterns of stress, flow, and vibration. You do not feel the pressure field of the air directly, yet it sustains your breathing. You do not sense the elastic stresses in the walls, yet they hold the roof above you. The invisible interplay of fields and matter silently supports your life, as it does for every living thing. As this day closes, you can take comfort in that thought. The walls around you, the air you breathe, the ground beneath you, all are participating in fields that maintain stability and balance. You do not need to hold everything together yourself. The structure of nature is already doing that. Let the weight of the day ease. Breathe steadily, allow your body to sink into rest, and trust the fields of the world to continue their quiet, steady work while you sleep. Chapter 10. From Classical to Quantum, the Legacy of Field Theory. Classical field theory began as a way to understand how forces and influences extend across space. From Newton's gravitational field to Faraday's lines of force and Maxwell's electromagnetic waves, fields became the language for describing invisible structures that shape the visible world. They turned space from an empty backdrop into an active player, filled with quantities that could carry energy, exert pressure, and propagate waves. But the story of field theory did not end with these classical successes. In the 20th century, the framework of fields became the bridge between the classical world of continuous media and the quantum world of discrete particles. The legacy of classical field theory is not just historical, It is the very foundation of modern physics. The first step in this transition came with the realization that light, which Maxwell had so elegantly described as a wave in the electromagnetic field, also behaved like a particle. Experiments at the dawn of the 20th century showed that light sometimes acts as if it arrives in discrete packets of energy, later called photons. This wave-particle duality seemed paradoxical at first, but it was reconciled through quantum theory. Fields, it turned out, could not simply be classical, continuous entities. They had to be quantized, their excitations appearing as particles. The electromagnetic field, when quantized, gave rise to photons. In this way, the field concept survived but transformed, becoming the basis of quantum field theory. The idea of quantized fields soon extended beyond light. Electrons, once thought of as indivisible particles, could also be described as excitations of a quantum field. The same was true for protons, neutrons, and eventually all known fundamental particles. Each type of particle corresponded to its own field, and interactions between particles arose from the interplay of these fields. What began as a classical framework for describing forces became a universal language for matter and energy. The continuity between classical and quantum fields is striking. Maxwell's equations, for example, remain valid in quantum electrodynamics, but they acquire new depth. The classical wave of light is understood as the collective behavior of countless photons. The field energy density introduced by Maxwell is still present, but it now includes contributions from quantum fluctuations. Even in a vacuum, the electromagnetic field is restless, filled with fleeting excitations that appear and vanish. Classical field theory anticipated this by treating fields as carriers of energy. Quantum theory revealed that this energy never completely disappears. This discovery led to profound consequences. If vacuum fields fluctuate, they can produce measurable effects. One striking example is the Casimir effect. When two uncharged metal plates are placed close together in a vacuum, the allowed quantum field fluctuations between them differ from those outside, producing a tiny but measurable force that pushes the plates together. This is not due to any ordinary pressure, but to the quantum energy of the vacuum itself. What classical field theory treated as empty space is, in the quantum version, a sea of activity. Gravity, too, reflects this legacy. Newton's gravitational field was reinterpreted by Einstein as space-time curvature, a field of geometry rather than force. Classical general relativity remains a field theory, though of a different type. Efforts to quantize gravity continue, seeking a theory where the gravitational field has particle-like excitations called gravitons. While such a theory remains incomplete, the logic follows the same path. The classical field must ultimately connect with the quantum framework. Classical field theory also shaped the way physicists think about symmetries. In electromagnetism, the invariance of the Lagrangian under certain transformations ensures charge conservation. This principle carried over directly into quantum field theory, where gauge symmetries dictate the interactions of particles. The electromagnetic field is just one example of a gauge field, and its quantum version explains not only light but also the forces that govern atomic nuclei. Without the groundwork of classical fields, these modern theories would lack their conceptual foundation. One of the most significant extensions of this idea is the Higgs field. Unlike the electromagnetic field, it does not carry waves that we see directly. Instead, it permeates all of space, interacting with particles to give them mass. In classical physics, mass is simply an inherent property of matter. But in quantum field theory, it emerges from the interaction between particles and the Higgs field. The discovery of the Higgs boson in 2012 confirmed this picture, completing one of the great triumphs of modern physics. Here again, the field concept proved its adaptability. What seemed like an abstract idea in classical theory became the explanation for one of the most fundamental aspects of reality. The legacy of classical fields is also technological. Radio, radar, fiber optics, electrical power systems, all these rest on classical field principles. But the same mathematics extends smoothly into the quantum devices of today: lasers, semiconductors, superconductors. In superconductors, for example, quantum fields describing electrons and magnetic fields combine to create effects like zero resistance and magnetic levitation. Even here, the classical concept of fields remains essential, translated into a quantum context. One might imagine that quantum theory erased the classical picture, but in reality, it built upon it. Classical fields are not wrong. They are approximations valid when quantum effects are negligible. Maxwell's theory of electromagnetism, for instance, works beautifully for designing circuits, antennas, and optical devices, even though at the deepest level light is made of photons. Similarly, classical elasticity theory describes bridges and skyscrapers accurately, even though the atoms inside obey quantum mechanics. The field concept survived because it was general enough to accommodate new discoveries. The unification of classical and quantum ideas through fields reached its most powerful form in the Standard Model of particle physics. This framework treats every particle as a field excitation and every interaction as a coupling between fields. The electromagnetic field, the weak nuclear field, and the strong nuclear field are all described in this way. The Higgs field, another invention of this framework, explains why particles have mass at all. Though quantum field theory is vastly more abstract than classical physics, its foundation lies in the same principle. Fields fill space. Fields interact, and the dynamics of fields explain the behavior of matter. Even the most exotic frontiers of physics continue to rely on this legacy. Cosmologists describe the early universe in terms of quantum fields, with inflation driven by a hypothetical scalar field that expanded space itself. Astrophysicists study plasma fields in stars and galaxies, where classical and quantum effects intertwine. The search for a theory of everything, whether through string theory or looped quantum gravity, begins with action principles and field-like descriptions. The path from classical to quantum has not replaced the concept of fields, but expanded it to encompass the entire known universe. And yet, even with this sophistication, the classical picture remains our entry point. When engineers design a radio antenna, they use Maxwell's equations, not the full machinery of quantum electrodynamics. When meteorologists model winds and currents, they rely on fluid fields, not quantized excitations. When physicians interpret X-ray images, they think in terms of classical waves interacting with tissue. Classical fields endure not because quantum fields are less accurate, but because they provide a language that connects directly with the scales of human experience. This continuity reminds us that science builds in layers. What once was thought final becomes a special case of something broader. Newton's gravity was refined into Einstein's curvature of space-time. Maxwell's waves became photons in quantum electrodynamics. Each layer adds depth, but preserves the validity of the previous one where it still applies. Classical field theory is not discarded, but embraced as the visible surface of a deeper reality. And here lies a quiet reflection. The same invisible fields that once explained falling apples and shimmering rainbows now also describe the restless quantum vacuum and the particles that form the fabric of matter. You are linked to the cosmos by these fields, continuous yet quantized, steady yet fluctuating, carrying energy and information across space and time. They are the threads that weave matter, light, and life into one unbroken fabric. As you close this chapter in thought, let that awareness ease you. The great theories of fields remind us that beneath change and complexity lies coherence, and that simplicity emerges even from the most intricate patterns. The same quiet laws that govern atoms and stars hold your world in balance. Let your mind soften, let your breath become calm, and allow the weight of the day to drift away into stillness. My friend, we've come to the end of our quiet journey through classical field theory and its legacy. If your eyes are still open and your mind is curious, you might enjoy another of my videos waiting for you, each one designed to guide you gently into sleep while unraveling the mysteries of the universe. But if you're already drifting, let yourself sink deeper into rest. Sweet dreams among the stars.